Welcome to the Deep Dive, the only place where we take a monumental stack of research notes and data and compress it down into the vital knowledge you need to walk away feeling truly informed.
Our mission today is highly ambitious. We're focusing on an increasingly popular but deeply controversial health trend, the meat-centric or carnivore diet.
And this is a topic of intense interest. We know many of you, especially if you're prioritizing metabolic health and, sustained vitality as you age, are really keen to understand these kinds of radical shifts.
Exactly. Can they truly deliver these profound health benefits people talk about? That's the core question.
It is. And we're holding a fascinating stack of sources today that, they don't just stop at dietary surveys. We're combining modern clinical outcomes with the deep history of human evolution and biochemistry.
We really are. We've got data from large social media surveys, some incredible anthropological insights from the Hadza and Inuit peoples, and then we're going to get into the weeds of our very strange genetic history.
Specifically regarding vitamin C, which is where this whole thing it gets really paradoxical.
It's the core conflict we are tackling today. It's a fundamental paradox of human biology that challenges, decades of conventional nutritional advice. How can a diet composed almost entirely of animal products be healthy long-term?
Right. When evolutionary biology tells us we absolutely rely on external sources for a vital nutrient like vitamin C, it doesn't add up on the surface?
It doesn't. If the carnivore diet works for some people, and the data suggests it does, where is the vitamin C coming from? And why on earth don't they all get scurvy?
That is the central mystery. We are connecting modern lifestyle choices that promise these radical improvements in conditions like type 2 diabetes, and we're tracing them all the way back to our deep evolutionary past, even down to the level of our chromosomes.
Yeah, and it forces us to look at the entire concept of nutrient requirement through a completely different lens.
A really different lens.
It does. It makes us ask if our ancestors found these nutritional workarounds that we, in the modern world, have completely forgotten.
And we'll use the data from the Hadza people, the Copper Inuit, and this story of the lost GULO gene to navigate what is really a physiological tightrope.
It is. Okay, let's unpack this and maybe start with the current trend.
Let's do it. Let's start with the modern context. When we talk about the carnivore diet today, we aren't talking about simply, cutting down on carbs for a bit. This is a very strict dietary pattern. For the sake of this deep dive, how are we defining it?
So we're looking at a pretty severe subset of what you might call low carbohydrate, high protein, or LCHP strategies, or even ketogenic strategies.
Okay.
It's characterized by an extremely high intake of animal-based products, so muscle meat, fats, and sometimes organs, and the nearly complete, if not total, exclusion of plant-derived foods.
And there's a philosophy behind it, isn't there? It's not just about food choices.
Oh, absolutely. It's often driven by a deeply held ideology, and that philosophy, as our sources suggest, is deeply rooted in a particular interpretation of human evolution.
Which is what exactly?
The underlying theory posits that early humans, especially after that big shift toward megafauna hunting, consumed a chronically low carbohydrate, high protein diet for a very long time.
And proponents argue this actually changed us metabolically.
Precisely. They argue that this long-term pattern positively selected for intrinsic metabolic traits, like a certain degree of insulin resistance.
Okay, you have to stop me there. Why would insulin resistance be selected for? Most modern doctors, and probably most people listening, view that as a severe negative, the first step towards diabetes.
In the modern context, yes. But in the context of deep time, it could have been a huge survival and reproductive advantage.
How so?
Think about it. In times of extreme scarcity, a famine or a brutal ice age winter, being highly efficient at using fat and protein for energy, while at the same time minimizing your glucose use and starch.
It would let you save what little glucose was available for the brain.
For the brain and other glucose-dependent tissues, exactly. It essentially provided a metabolic buffer against starvation. It was a feature, not a bug.
That is a powerful evolutionary argument, but how does that translate into the modern experience? And this is where it gets really interesting. We have the real-world results from a major 2020 social media survey.
Yeah, and I want to be clear, this wasn't a randomized controlled trial.
Right.
But it's a crucial data set. It's a snapshot of the population actually engaging in this trend. The study included 2,029 adult respondents with a median age of 44.
And skewed heavily male, I noticed.
Very heavily male, 67% were men. And importantly, the median duration they had followed the diet was substantial, 14 months. So this is not a fleeting 2-week experiment these people are doing.
Okay, so why? Why were these people making such a radical life change?
The motivation was overwhelmingly for health reasons. A massive 93% of participants reported that. They weren't just doing it for, say, weight loss, although that definitely occurred. They were often seeking relief from complex chronic issues.
Well, what did their daily meals actually look like? Was it just steak and eggs for a year?
For many, it was pretty close to that, yeah. The dietary details confirmed just how strict it was. 85% consumed red meat daily, or even more often.
Wow.
And this is the crucial part. Less than 10% reported consuming vegetables, fruits, or grains, even on a monthly basis. This extreme exclusion of plants is what underscores the core question we're trying to answer today.
And the most surprising part for me, for anyone worried about, compensating for missing nutrients from plants,
Right.
37% did not use any vitamin supplements at all.
None. They were relying entirely on the food.
That fact alone would make most traditional nutritionists just gasp,
Eh.
which is why we have to examine the outcomes so carefully. Let's look at the reported aha moments, the benefits that drove this popularity, especially for the metabolic issues that worry older adults.
Well, the overall satisfaction levels were exceptionally high. You had participants reporting improvements in overall health at 95%, and general well-being was also way up, ranging from 66% to 91%. But the physiological changes were also really notable.
The anthropometrics alone, the body measurements, suggest a major shift in body composition.
Indeed. The median body mass index, or BMI, decreased significantly. It moved from 27.2, which is just on the border of overweight,
Right.
down to a healthy 24.3. That suggests substantial sustained weight loss across this whole group, which is a major factor in, overall longevity and reduced stress on joints and the cardiovascular system.
And for individuals who are managing type 2 diabetes, a condition that can severely compromise quality of life as we age, the data seems, almost revolutionary.
The data on diabetes outcomes are perhaps the most compelling part of the survey.
Absolutely. Participants with diabetes reported significant improvements.
Okay, like what?
They saw a median reduction in their glycated hemoglobin, or HbA1c, by 0.4%. Now, while 0.4% may sound like a small number in isolation, you have to consider that this change was achieved alongside a dramatically reduced reliance on medication.
Okay, so how dramatic was that reduction in meds?
The reported numbers are just staggering. Participants reported dramatically reduced diabetes medication use, with percentages ranging from 84% to 100%.
100%. So some people got off their meds entirely.
That's what they reported. And for many aging individuals, the prospect of managing or even reversing type 2 diabetes without the burden of constant pharmaceutical intervention is a huge draw. It represents both independence and renewed health. It paints a very positive picture. Quick, satisfying metabolic gains for a lot of these users, but, playing the skeptical proxy for you, the listener, I have to ask, every extreme diet has risks. We have to look at the other side of the ledger,
Of course.
particularly cardiovascular health, which is, it's the paramount concern for longevity.
That is the necessary critical engagement this data demands. And you're right to go there. One of the unexpected findings was the low prevalence of reported adverse effects. Most issues were transient, like mild GI symptoms.
Right.
But the data on cardiovascular markers presents a significant unavoidable conflict, a real problem.
Okay, lay out the conflict for us.
The data is a true dichotomy. On the positive side, the high-density lipoprotein, or HDL, the so-called good cholesterol.
Yeah.
The levels reported were optimal, averaging 68 mg/dL. Triglycerides were also excellent, also averaging 68 mg/dL. These two markers are strongly associated with lower heart disease risk. If you only looked at HDL and triglycerides, this diet appears cardioprotective.
There's always a but.
But then we confront the elephant in the room, LDL cholesterol.
The bad cholesterol.
That's right. The low-density lipoprotein, or LDLC, was found to be markedly elevated, averaging 172 mg/dL in the subset of people who reported their lipid data.
172. That's a level that immediately raises red flags for any conventional cardiologist. Elevated LDL is a known primary risk factor for atherosclerotic heart disease.
It is, absolutely.
So how do you reconcile that? How can you have dramatically improved diabetes markers, which is great for your heart, with dangerously elevated LDL? That seems like you're just trading one risk for another.
It introduces a profound nuance into how we think about cholesterol metabolism. Our sources acknowledge that a diet rich in red meat and saturated fat can increase LDL cholesterol. No one denies that. However, the exact extent of that increase is described as highly individual.
Meaning it affects everyone differently.
Massively differently. We have to consider that for a small subset of people, often called lean mass hyperresponders, their LDL reaction to saturated fat is far more exaggerated than the average person. But for the general cohort, while the average is high, it requires a deeper look than just that total number.
What do you mean? Are you saying that the high LDL number might not carry the same risk if other things like inflammation markers and triglycerides are low?
That is the ongoing and very heated debate. When your triglycerides are very low, like 68, and your HDL is high, it often suggests a pattern of less dense, maybe less atherogenic LDL particles. The LDL might be elevated, but the quality and size of the particles may be less harmful.
But we don't know that from this survey.
We don't. And that's the key. Without particle number or particle size data, that 172 milli-GDL average remains a definitive warning sign. It must be managed, especially for any of you listening who are already concerned about heart health. This is why testing is absolutely non-negotiable on a plan like this.
Okay, so beyond the cardiovascular system, what about the processing strain? This massive protein and fat load must put a strain on other vital organs, specifically the kidneys. This is a major concern for older listeners, as kidney function naturally declines with age anyway.
This is a critical warning we have to highlight, and it's drawn from studies on similar LCHP patterns. The consumption of such a diet delivers a marked acid load to the kidney. When you break down high amounts of protein, it produces non-volatile acids that the body has to clear.
And what's the immediate physiological consequence of that acid load? What does it do?
We have data from other studies showing that over just a 6-week period on an LCHP diet, urine pH dropped significantly from about 6.1 down to 5.5 in the induction phase. That's a big shift towards acidity.
So the kidney has to work overtime to excrete all this acid.
Dramatically over time. Net acid excretion increases dramatically.
A drop in urine pH combined with that high protein load.
Mm.
That sounds like a perfect recipe for kidney stones.
It absolutely is. Our sources highlight 3 specific factors that increase kidney stone risk. First, that low urine pH you mentioned. Second, urinary citrate levels decrease.
And citrate is a good thing.
Citrate is a natural inhibitor of kidney stone formation, so less citrate means less protection. And third, the urinary saturation of undissociated uric acid increased more than 2-fold.
So you've got high acid, a low inhibitor, and high uric acid saturation.
It's the trifecta. These combined factors significantly increase the risk for kidney stone formation. And for aging kidneys, which may already be working with reduced capacity, placing this intentional continuous acid load on them requires really careful consideration and monitoring.
That is an extremely important caution for anyone considering this long-term. And you mentioned a third issue related to this acid load.
Yeah.
Bone health.
Bone is a major buffer for systemic acid. If the kidneys can't excrete all the acid, the body can leach alkaline minerals, primarily calcium, from the bone structure to neutralize the load.
So it's literally pulling calcium out of your bones to deal with the acid from the diet.
That's the concern. In the LCHP study we're referencing, urinary calcium levels increased significantly. The body was just peeing out more calcium.
Did the body compensate for this loss? Like, did it absorb more calcium from food?
Not effectively, no. This increase in urinary calcium wasn't offset by better calcium absorption in the gut. The estimated calcium balance decreased, and markers for bone turnover trended upward.
Which suggests what, long-term?
It suggests that this kind of chronic, high acid load may increase the risk for bone loss over time. This metabolic shift is particularly critical for older adults, especially postmenopausal women who are already battling osteoporosis or osteopenia. The high-protein strategy has to be balanced with ways to mitigate this acid load, or it could compromise your skeletal integrity.
Okay, so we've established that the modern, muscle meat-heavy carnivore diet carries both these profound metabolic benefits, but also significant specific risks. Kidneys, bone density, LDL cholesterol. This leads us perfectly to the ancestral argument. The success of a pure animal-based diet in history, avoiding scurvy, maintaining strength. It must hinge not just on what they excluded, but critically on what parts of the animal they ate. Ancestrally, they weren't just eating filet mignon.
That is the essential pivot point in this entire discussion, the nutritional hierarchy of animal products. We have to move beyond the, comparatively nutrient-poor muscle meat and look closely at the role of organ meats, or offal.
And this wasn't an accident.
Not at all. The ancestral practice globally documented among the Hadza of Tanzania, the Copper Inuit in the Arctic, various indigenous American groups, was to utilize the entire animal, often consuming specific organs raw or just very quickly prepared.
So this wasn't just about subsistence or reducing waste. It was strategic. It was high-level nutrition. They were accessing nutrient density that was totally unavailable in the muscle tissue alone.
Exactly. And to illustrate this, the source material gives this detailed and fascinating anecdote from the Hadza people. After a successful large game hunt, they perform a specific post-hunt ritual. Specific, highly prized organ meats are reserved for a select group of men known as ipim.
And who qualifies as IPIM? Who gets the good stuff?
They are the successful strong hunters, typically in their prime age range of 20 to 25. But here's the critical sociobiological insight. Even if a man stops hunting successfully, by the time he reaches 30 to 35 years of age, he automatically becomes considered ipim.
Wait. So the society essentially changes the rules to ensure the older men still get the best nutrients, even if they aren't the best hunters anymore.
Precisely. This social practice ensures that all men, including the older men in the community who still contribute wisdom and experience but may not have the hunting success of a 25-year-old, receive a guaranteed ration of that fat and vitamin-rich meat over time.
That's a profound, culturally enforced mechanism for nutrient distribution. It safeguards the vitality of the elders.
It's a biological insurance policy that modern society completely lacks.
That is a stunning piece of evolutionary and social context. It shows they understood the value of nutrient density implicitly. Let's define that term rigorously here for a second.
Nutrient density is defined simply as the amount of bioavailable nutrition per calorie. If you imagine a scale, on one end you have high-calorie, highly processed foods with near zero nutrient density.
Right, empty calories.
And on the other end, you have organ meats. The source material positions organs, particularly the liver, as some of the most nutrient-dense foods on the planet. They contain concentrations that just far exceed the nutritional yield of a similar volume of muscle meat.
So a small serving of liver can have more nutrients than a whole day's worth of food for some people.
It can literally exceed the daily nutrient intake of many people consuming a standard Western diet.
Yes. Okay, let's get into the specifics then. What exactly makes organs the nutritional superstars compared to the muscle meat we typically consume? We've got data here detailing the profiles of liver, kidney, and pancreas.
Well, if we look at the overall profile, organ meats contain abundant bioavailable B-complex vitamins, crucial fat-soluble vitamins A, D, E, and K2, and essential trace minerals like iron, copper, and magnesium.
And the good fats, too.
And they often carry a beneficial omega-3 to omega-6 fatty acid ratio, especially in the fat surrounding the organs. These are the very nutrients most likely to be missed in a plant-restricted diet.
The liver stands out immediately in the data. I mean, it's a true micronutrient bomb.
It absolutely is. Per 100 grams, raw beef liver delivers a staggering 16,899 international units, IU, of vitamin A.
Wow.
This is crucial not just for vision and immunity, but for cell replication and differentiation. It also provides 59.3 micrograms of vitamin B12, essential for nerve function, and 290 micrograms of folate.
And for our older listeners who might be concerned about cognitive function and brain maintenance, that choline content is also remarkable.
Yes, liver provides 333 milligrams of choline, which is a precursor to the neurotransmitter acetylcholine. These concentrations are just profound. To put 59.3 milligram of B12 in perspective, the typical daily requirement is around 2.4 milligrams.
So liver is delivering 20 times that in a single serving.
More than 20 times. This level of nutrient concentration is exactly why ancestral people prized it so highly.
What about the other organs? They all seem to contribute something unique to the full nutritional spectrum.
They do. If we look at the kidney, it's the highest source of the trace mineral selenium, providing 141 micrograms per 100 grams. Selenium is a vital cofactor in antioxidant pathways and thyroid function.
And interestingly, kidney has some vitamin C.
It does. It provides a small but notable amount, 9.4 milligrams. And this starts hinting at the solution to that scurvy paradox we're going to get to.
And speaking of surprising sources, let's look at the pancreas. It provides the highest fat content among the organs in our table.
The pancreas, which we, rarely consume in the modern Western diet, is relatively high in total fat, about 18.6 grams per 100 gram. It's also significantly rich in omega-6 fatty acids, But, crucially,
It has the most vitamin C.
it provides the highest recorded vitamin C content of the four organs, coming in at 13.7 milligrams per 100 grams.
So the answer to the immediate nutritional deficiency question, where do you get nutrients when you restrict plants, is not complicated, but it is culturally very difficult for modern eaters.
That's the core takeaway from this section. Ancestral wisdom ensured full-spectrum nutrition by utilizing this diversity of organs. Modern analysis confirms that these organs are concentrated powerhouses that specifically fill the micronutrient gaps created by muscle meat-only consumption.
And without this intentional inclusion of organs.
Without it, long-term deficiencies are almost guaranteed, regardless of the diet's efficacy for weight loss or glucose control.
This brings us to the most complex and fascinating part of our deep dive. The vitamin C conundrum. The carnivore diet seems to work for some people. The Hadza and Inuit thrived on animal-based diets. And yet, every single textbook says we need vitamin C, ascorbic acid from plants to avoid a devastating disease like scurvy. Let's unpack this with genetics. What makes humans so incredibly vulnerable to vitamin C deficiency?
The vulnerability lies in a critical genetic defect. Unlike nearly all other mammals, humans, and other higher primates, so tarsiers, monkeys, and apes, along with guinea pigs and some bats, cannot synthesize vitamin C internally. We are totally reliant on our diet for it.
And this inability is due to a single broken gene. Tell us about the L-galanogamma-lactone oxidase gene, or GULO.
The GLO-ZU gene is crucial because the enzyme it codes for catalyzes the final rate-limiting step in the internal metabolic pathway that converts glucose into vitamin C.
So we have the gene, but it doesn't work.
We possess the GUO gene. It's located on chromosome 8, but it's a pseudogene, a non-functional copy that's just riddled with mutations and premature stop codons. It's essentially a piece of metabolic machinery that rusted and broke down millions of years ago.
Why on earth would we lose such a vital capability? I mean, that sounds like a colossal evolutionary blunder. It invites a potentially fatal deficiency like scurvy the moment your fruit sources disappear.
It seems totally counterintuitive, right? But the Ladding theory suggests it was either a neutral mutation that wasn't selected against, or perhaps it even provided a subtle evolutionary advantage.
The advantage.
By saving metabolic energy. The biosynthesis pathway to produce vitamin C is highly energy intensive. It requires not just glucose precursors, but also significant amounts of ATP and cofactors like NADPH.
Okay, so let's paint the picture. If our early primate ancestors were living in a consistently resource-rich environment, a rainforest, maybe, where fruit dominated their diet and provided massive, continuous doses of dietary vitamin C.
Then the body was receiving all the vitamin C it needed externally. In that context, the mutation that disabled the energy-intensive GLO enzyme would have conferred a selective advantage.
Because it saved metabolic energy that could be used for other things.
For other survival or reproductive functions, exactly. It was a genetic trade-off. Give up internal production to save energy because the supply is guaranteed from the environment.
And when did this evolutionary trade-off happen? How long ago are we talking?
The loss of synthesis capacity is believed to have occurred very early in primate history, around 60 million years ago. And the timing is critical because it precedes the split between the Strepsirini-like lemurs, which can still synthesize VC, and the Haplogene, which includes all monkeys and apes, who became entirely reliant on diet.
And once it was lost, the capacity never came back.
Never returned.
So we lost the ability to make it, but we developed this brilliant compensation mechanism to retain and recycle every possible scrap of the vitamin C we consume.
Tell us about that evolutionary hack. This is the hypothesis that solves half the paradox. It's theorized that the loss of GLO was compensated by the acquisition and optimization of something called the GLUT1 transporter.
Which is located where?
Prominently on our red blood cells.
And what does GLUT1 typically do? And how does it relate to vitamin C?
So GLUT1 is primarily a transporter for glucose. But, crucially, it also transports the oxidized form of vitamin C, which is called dehydroascorbic acid, or DHA.
The oxidized form. What does that mean?
When ascorbic acid performs its function as an antioxidant, it gives up an electron and becomes oxidized into DHA. The body can't afford to lose that DHA molecule.
So GLUT1 scoops up the used vitamin C.
Exactly. The GLUT1 transporter acts as an incredibly efficient salvage and recycling system. It captures the DHA, transports it back into the cell, where internal reducing agents like glutathione quickly convert it back into active ascorbate.
So this recycling mechanism is so powerful and allows the body to maintain high concentrations of active vitamin C with a very low external intake.
That's it. That efficiency fundamentally changes the nutritional requirements of a human compared to, say, a goat, which can make its own.
How much less do we need because of this?
This adaptation meant that GLUT1 expressing individuals needed far less dietary vitamin C to avoid severe deficiency. Some estimates say up to 100-fold less than some species without this recycling mechanism. It's a powerful evolutionary offset to the GULO loss.
This genetic efficiency leads directly to the ultimate historical test case, the Inuit paradox. For centuries, European explorers on long voyages or Arctic expeditions, subsisting on canned rations devoid of fresh produce.
They suffered devastating scurvy. Their symptoms were awful: poor wound closure, bleeding gums, joint pain, all related to compromised collagen synthesis. And we know scurvy can be prevented by as little as 10 milligrams a day of vitamin C.
Yet the indigenous copper Inuit living in the exact same harsh Arctic environment on a near-exclusive meat and fat diet historically did not suffer from scurvy. Meanwhile, the explorers, with all their technology, just succumbed.
It was a true scientific mystery for decades.
And the mystery is only resolved when we understand that a meat diet doesn't mean muscle meat only, and that preparation really, really matters.
Absolutely. The resolution is that the traditional country food consumed by the Inuit, which included raw and quickly prepared animal parts, did indeed provide sufficient vitamin C. It was just enough to leverage the body's highly efficient recycling system.
Can you give us a concrete example of those surprising sources?
The most frequently cited source is muktuk, which is raw whale skin and blubber.
Raw whale skin.
Raw whale skin. And it's documented as an excellent source, having vitamin C levels comparable to a glass of orange juice. This is the kind of surprising fact this deep dive lives for, that nature packed a powerful micronutrient punch into something completely counterintuitive to the Western palate.
That turns the conventional view of health food completely on its head. What other organs or tissues were providing that essential VC?
Seal liver provides about 24 milligrams per 100 gram, and brain tissue provides around 15 milligrams per 100 grams. The key factor here, and this is why cooking muscle meat fails to provide it, is processing. Vitamin C is highly heat sensitive.
Cooking destroys it.
Cooking reduces the content, often substantially.
But wait, didn't some explorers, like Stephenson, supposedly cure scurvy with boiled and frozen meat?
Yes, but the success there likely depended on the fact that he was consuming raw or frozen organs and fat, or even raw frozen muscle meat, alongside the cooked portions. The sources note that even if it's cooked, the loss of vitamin C is reportedly smaller in animal-derived food compared to plant-derived food.
Why is that?
The thinking is that the animal tissues, the matrix of the food, protect the ascorbate better from heat degradation.
Okay, finally, let's tie this all back to the modern metabolic discussion from Section 1. The GULO loss happened because of abundant glucose from fruit, but the carnivore diet removes glucose.
And that is the ultimate metabolic connection. Most vitamin C demands, its role as an antioxidant, are intrinsically linked to carbohydrate and glucose metabolism. The prevailing hypothesis is that a traditional low-carb, high-fat diet, which is naturally low in glucose, might fundamentally lower the absolute required intake of vitamin C needed for survival.
So by removing the high glucose load, you reduce the metabolic stress and maximize the efficiency of that GLUT1 transporter we talked about.
Exactly. For those of you trying to manage glucose and insulin levels today, this suggests a powerful synergy. A reduced glucose environment may mitigate the risk of VC deficiency, even on a restricted diet.
Building on that metabolic connection and the efficiency of the GLUT1 system, let's bring vitamin C into the modern clinical arena. Let's focus on its complex roles in the body. This is highly relevant to understanding its potential therapeutic application in chronic disease and aging. What are the dual, seemingly contradictory roles of vitamin C in our physiology?
Vitamin C uniquely plays both an antioxidant and, surprisingly, a pro-oxidant role. It depends entirely on the concentration and the context.
Okay, so let's start with the familiar one, the antioxidant.
In its primary well-known capacity, it is the master water-soluble antioxidant. It neutralizes free radicals, it reduces lipid peroxidation in your plasma and your LDL, and it plays a vital role in recycling vitamin E back into its active form. It's a major component of the body's internal shield against cellular damage.
So where does the pro-oxidant nature come in? That sounds totally counterintuitive, especially if we're talking about fighting aging.
The pro-oxidant role is strictly pharmacological. This is really important. It means it's only observed at the incredibly high concentrations you can only achieve through intravenous vitamin C administration, especially in cancer research.
So you can't get this effect from eating oranges.
No, not
Oh.
even close. In this context, these high doses act as a prooxidant by generating hydrogen peroxide, H2O2, directly within the extracellular fluid.
And why would generating hydrogen peroxide be a good thing?
Well, H2O2 is toxic to cells, but normal, healthy cells can effectively neutralize it. However, the high concentrations of H2O2 generated by IV vitamin C have been shown to selectively decrease the growth of aggressive tumor xenografts in mice.
So it's selectively toxic to cancer cells.
That's the theory being studied. It's a significant area of research, sometimes showing synergy when combined with traditional chemotherapy drugs like gemcitabine or cisplatin. It just illustrates that vitamin C's function is entirely dose-dependent and highly, highly complex.
That distinction between dietary intake as an antioxidant and therapeutic IV use as a prooxidant is absolutely vital for you to understand. Now let's return to the interaction with diet, specifically glucose, which is profoundly relevant for our aging listeners managing blood sugar. We need to fully unpack the glucose-ascorbate antagonism, or GAA.
The GAA theory is central to modern metabolic health, and it links directly back to our evolutionary discussion about those GLUT transporters. It relies on a simple molecular fact. Glucose and ascorbate vitamin C have similar molecular structures.
They look alike to the cell's transporters.
They do, and because of this structural similarity, they compete for entry into cells via the same transport mechanisms, primarily the GLUT transporters.
Okay, let's use a tangible analogy to make this mechanism crystal clear for everyone.
Imagine the GLUT transporter as a busy toll booth on a highway. Vitamin C is a small, efficient car trying to zip through. Glucose, however, is a massive, slow line of fully loaded 18-wheeler trucks.
Okay.
When traffic is light, meaning your blood sugar is low, that small vitamin C car can get through easily. But if someone has chronically high glucose levels, if there is a mile-long traffic jam of trucks, that high glucose physically clogs the toll booth, impeding vitamin C's entry into the cell.
That is a staggering implication for managing chronic diseases like type 2 diabetes. High blood sugar doesn't just damage tissues directly, it actively blocks the entry of a critical protective nutrient.
Exactly. And this theory aligns perfectly with clinical observations. For example, vitamin C levels are found to be inversely related to obesity, which is often a correlate of increased carbohydrate intake and subsequent hyperinsulinemia.
So the more carbs you eat, the lower your vitamin C status might be, functionally.
Functionally, yes. Impaired uptake of vitamin C in diabetic patients is well documented. This compromised uptake can critically impair immune function and even lead to an acute scorbutic status like actual scurvy in critically ill patients, even if they have adequate dietary intake, simply because the body can't absorb and utilize it efficiently.
So the high-carb environment of the modern Western diet artificially increases our functional need for vitamin C because the glucose is jamming the transport mechanism, forcing us to try and outcompete it with higher intake.
That is the key takeaway for metabolic health. The body has to deal with two competing demands, and if glucose dominates, vitamin C loses. But there's another layer to this efficiency within the cell. We mentioned dehydroascorbic acid, DHA, the oxidized form of vitamin C.
Right, the form that GLUT1 transports into the cell for recycling.
Correct. So DHA enters the cell and is quickly transported into the cell's powerhouses, the mitochondria, via GLUT1. Once inside the mitochondria, it is rapidly reduced back to active ascorbate by internal agents like glutathione or GSH. This internal localized recycling mechanism is absolutely critical.
Why is mitochondrial protection so vital, especially for aging?
Mitochondria are where oxidative damage is most often generated as a byproduct of making energy. This internal vitamin C recycling protects the mitochondria from this constant damage.
And mitochondrial dysfunction is at the root of a lot of age-related diseases.
It's a recognized key factor in a wide range of them, from neurodegenerative diseases like Parkinson's and Alzheimer's to general decline and sepsis. So maximizing the efficiency of this VC recycling system is paramount for cognitive function and cellular vitality as we age.
Let's pivot to how vitamin C directly impacts cardiovascular health, which is a top priority for our longevity-focused audience, and also tissue repair, starting with CVD.
Observational studies consistently show a strong correlation here. Higher plasma vitamin C concentrations are associated with a lower risk of stroke, specifically cardioembolic stroke. Furthermore, clinical trials involving supplementation in hypertensive patients have demonstrated that it can reduce blood pressure and improve blood flow and vascular function.
And there's a specific mechanism cited for how vitamin C might directly help lipid profiles beyond just its general antioxidant role in protecting LDL particles from oxidation. This brings us back to the complex high LDL results we saw in Section 1.
This is a crucial finding, and it provides a potential countermechanism to that high LDL problem. Research has demonstrated that vitamin C can inhibit the expression of a protein called PCSK9.
Okay, and why is that important? What does PCSK9 do?
PCSK9 normally causes the degradation of LDL receptors, or LDLR, on the surface of liver cells. These receptors are what pull LDL out of the blood.
So if vitamin C inhibits PCSK9,
It allows more LDL receptors to remain active on the liver surface. More active receptors means the liver can more efficiently scoop up and clear LDL cholesterol from the bloodstream.
so in theory, vitamin C supplementation could actually lower LDL.
It could improve lipid profiles and potentially reduce CVD risk, particularly in individuals who are deficient. This mechanism is one reason why an ancestral diet rich in bioavailable VC from organs might mitigate the theoretical risk of high LDL associated with high saturated fat intake. It's a balancing act.
Finally, let's touch on wound and tissue healing. This is critical for post-surgical recovery, maintaining skin integrity, and just physical resilience as we age.
Vitamin C's role here is foundational. It acts as an essential cofactor in synthesizing collagen. Collagen is the most abundant protein in the human body. It provides tensile strength to all your connective tissues, blood vessels, bone, skin, cartilage.
So without sufficient vitamin C, the body cannot form strong, stable collagen.
Exactly. That's the root cause of the physical symptoms of scurvy, the bleeding gums, the wounds that don't heal.
And what about modern applications for accelerating healing?
Modern therapeutic strategies frequently employ topical or high-dose oral supplementation, often at doses like 1,000 milligrams a day, to promote fibroblast activity. Those are the cells that generate connective tissue and accelerate healing.
I've also heard it can reduce scarring. How does that work?
It does that by modulating a pathway called the hypoxia-inducible factor 1, or HIF1 pathway.
Okay, what does that pathway do?
So HIF1 is activated under low oxygen conditions, such as those found in deep wounds, which can lead to poor, slow healing and more scarring. By downregulating this factor, vitamin C helps combat the negative effects of that chronic hypoxia and promotes faster, better tissue regeneration.
Is there data on this?
Yeah, the data shows that even severe, slow-healing wounds like abdominal wounds that fail to close after surgery can see considerable reduction and eventual closure after supplementation is initiated. It's a profound functional role that is essential for maintaining physical integrity throughout life.
We have covered a huge amount of ground today, integrating modern clinical trends with deep evolutionary biology. Let's synthesize the 3 key actionable takeaways for you, our learner.
First, the modern meat-centric diet is producing some surprisingly positive health outcomes, particularly in these dramatic metabolic improvements like diabetes reversal. We're seeing massive medication reductions and high satisfaction.
Right.
But this approach demands extreme caution and monitoring. You have to be aware of the conflicting cardiovascular markers, specifically that elevated LDL, and the risk of increased kidney stone formation and potential bone loss caused by the persistent acid load.
Second, the sustainability of an all-animal diet rests entirely on recognizing that ancient nutritional wisdom. You have to consume organ meats, not just muscle.
That's right. These organs are nutrient powerhouses. They provide the vitamin A, B12, choline, and trace minerals that muscle meat lacks. They are the essential key to bridging that nutritional gap and avoiding deficiencies like scurvy.
And third, the vitamin C paradox is resolved through both evolution and behavior. We lost the GULO gene millions of years ago, but we compensated with the incredibly efficient GLUT1 recycling mechanism, meaning we need far less than other species for basic survival.
Crucially, that need is intrinsically linked to our overall metabolism. The less glucose you consume, the lower your potential vitamin C requirement. You remove that glucose-ascorbate antagonism.
This leaves us with a final provocative thought for you to consider as you digest all this information. Historically, some dissenting scientists have argued that the optimal daily intake of vitamin C should not be based merely on the minimum required to prevent scurvy, that tiny 10 milligram day minimum.
Right. They argued it should instead mirror the high amounts produced internally by the vast majority of mammals that can synthesize it. For a healthy adult human, this internal production was estimated to be 2.3 grams or more per day.
A completely different order of magnitude.
Completely. So considering the profound individualized impact of glucose metabolism, that toll booth competition we talked about, and our own specific genetics, including the highly efficient GLUT1 transport capacity, The question for you is this.
Is simply meeting the minimum daily requirement to prevent scurvy truly enough to optimize your health and longevity? Or should we be reevaluating our intake based on our unique genetic heritage and our current metabolic status, maybe aiming for higher, more therapeutic levels?
That is a question worth exploring further in your own research.
Thank you for diving deep with us. We'll see you next time.
Until then.